input of the light ray. So hence, you have less exposure for the H. Okay. So that's is a phenomenon called exposure fall off. Later on, we will have a slide to talk about that. So you don't need to like write it down right now. All right, those are the two things that you can observe. And the other thing is, if you zoom in to the specific region, for example, like the red region over there, if you zoom in, then you can observe the relief displacement. So as you can see, the building lies down, and then you can also link back to your knowledge that you have learned in this class. First is what's the direction of the relief displacement? It's using the let me ask you guys. What's the radial center for the relief displacement? Listen. Let's check if you have watched the videos. What's the radial center for relief displacement? All right, give you three choices. Principal point, isocenter, nadir point, image nadir point, principal point, and also isocenter. So, which one is the radial center to the relief displacement? Okay, great. Nadir point, right? Because the relief, if it's a nadir point, doesn't matter it's a tilt photo or vertical photo. The nadir point means that directly from the principal perspective center to the vertical line. And in this case, if there is any like elevation changes along this line, then it doesn't matter. It will project to the same nadir point. So there's no relief displacement. The relief displacements on the image nadir point. So it is using the nadir point. Relief displacement is using the nadir point as the radial center. So the farther away from the nadir point, then you have larger relief displacements. And also the size of the relief displacement is also affected by the building height, of course. You can say, or you can say the object's height. And the location of it, yeah, like I said, farther away from the nadir point, it will be larger. Any other things? And also the tilt angle as well. If you are talking about the tilt photo, then tilt angle also affects the relief displacement, the size of it. Right, so that's the other thing that you can observe when you zoom into the details. And here is talking about discussing the relief displacement. If you are talking about, say, how to transform the central perspective image to the map, then relief displacement is a noise that we want to remove. And then we couldn't even just use the DEM to remove that. We need the additional information like the DBM, digital building model, to perform true auto-replication to remove the relief displacement from the buildings. So that is the noise in terms of that. However, if you are doing some three-dimensional precisioning to obtain the object space coordinates, then in this case, relief displacement is talking about is the information that you have. Like I said, is the larger of the relief displacement. It kind of indicates that it has a larger elevation. There's a larger elevation change over there. Okay. Right, and here is talking about the applications. Well, there are many applications, like I said, and we can just take a look at by yourself. And then here is the history and the development, which I didn't mention too much during the lectures. But the trend is kind of like that, from the convergence of photographing and then to analog stereo photogrammetry, analytical photogrammetry, and to the digital photogrammetry right now. So the trend is to become more automatic and also have better precision and accuracy. So this is one of the way in the very, very past. So this is the, this painter, or this artist, you can say, or painter. So basically, he's drawing this old man, and then but however, there's a interesting instrument that he's using. He's using an instrument to block one of his eye. Okay, so he will draw two images, draw two drawings. One is by blocking his left eye to draw one, and the other one is blocking his right eye to draw the other one. So which indicates that you will have two drawings, and those two drawings indicates the images that you have taken by your left eye and the right eye. Okay, so two images, and in this case you can draw something like this. And after you draw something like this, what you can do is one interesting thing is if you have the slice, then you can try to force. Okay, what if you have that you have that slice, then what you can do is like this, and then try to force your right eye to look at this. Try to force your left eye to look at this. Like I don't know what's the term in English. Just to in Chinese it's 斗鸡眼. How's cross? Yeah, kind of like that. Just cross eye. Cross eye. So to force your like right eye to look at it and left eye to look at it. And if you find the proper intersection angle, then you can see the you can see the you can see elevation differences, or you can see the stereos. The depth, yes, you can see the depth, yes. Alright, so that's what the photogrammetry was in the past, before we have camera. Alright, and this is also before we have camera. Actually, like I described in the past, the photogrammetry work is the first first application of photogrammetry is to measure the terrain elevation differences. So, but however, in the past, if you are going to use the ground surveying to measure that, it's very difficult. So they put people on the hot balloon and then try to measure the distance and also the angle to draw. For example, like these are the two the location of two hot balloons, and then if you find the same feature over there, then you will measure. Okay, so what's the angle of it, and then what's the distance of it, and then to measure the elevation differences and also the location of those features. So that's the mapping work. But as you can imagine. Right now, we can replace those things, those surveyors and also hot balloons with airplane and also camera. So that's much more efficient in this case. Okay, so and here is the analog age. So you will have two film. So after you take the photo, you have the film over here, and then you will project to the to the canvas, and then you will have there's a surveyor to operate this machine, and then to start drawing, for example, the elevations. Okay. And this is the analytical. I believe this is this is an analytical plotter. So you also have two films. Then two stereo pairs. One stereo pairs with the two films over here, and then you will project it to this canvas. And then here's like reaction wheel, and then you can like rotate it and then to intersect them. And correspondingly, you can draw the maps over there. And this is also an analytic plotter, one of the example. And this is the current working station, that digital working station that we have nowadays. Actually, I believe you guys see that in the on the Thursday lab. Actually, that's the lab. In that lab, actually, there are two stations over there. So, just like that. If you are interested, you can go there and take a look. Okay. So this is the whole processing and processing of the aerial photogrammetry work. So, for example, like if right now you want to like create a map or to know the elevation of the certain region, for example, in you can say Taoyuan city, for example. And the first thing that you need to do is actually you need to plan the flight trajectory. And then usually, like I said, the flight trajectory is usually like this, like the Z shape. And sometimes one direction is not enough. People will also design another direction to do that. Right. So, and that's to plan the flight route. Okay. So basically, it's like that. And so that's the first step. And then the second step is the image acquisition. So you just fly the airplane and then take the photos. And after you collect that, the third one is the control surveying. Because, like I said, you take the photo and then of course, you can have some initial EOP from the sensors and from the GPS and from IMU. But however, those initial EOP contains errors. And in this case, if you directly utilize those information, then you will result in you will find out that you have more error in your final result, and especially the information that you have may result in, say, you are in a certain coordinate system that is not the actual coordinate system. So it's kind of like we need to register the whole system to the real world location. So in order to do that, we need the actual control points. So how to obtain those control points? We need the control survey. So we need to either use GPS or use some ground surveying tools to measure some of the points over there in the you can say AOI, area of interest. You need to measure some of the control points. Okay, with those control points, then you can perform the photo triangulation, 空中三角测量 photo triangulation that we talked about before. So, and then you also can measure some of the, you also, of course, you can measure some of the, you can also measure some of the tie points, and then you can also obtain their object space coordinates. And then in this case, the whole image, the whole area of interest can have the multiple, lots of you can say object space coordinates. Okay. So and then in this case, that's the photo triangulation. The photo triangulation mainly means over here. Mainly means to correct the orientation. And then you are plotting, and then you are going to measure the tie points, and then you can create the digital elevation model. And then with that, you can create the also image. And finally, you can edit the also image and to digitize it to become a map. So that's the whole process for the general area photogrammetry work. Okay. Okay, so that's about it for the first chapter. Any question? It's quite well. It's kind of like the introduction. Should be easy to understand and follow. Alright, still, I'm going to go over that. However, some of the content are too detailed. Maybe I won't talk about the detail of that. For example, like this. And this is talking about the chapter 2 is talking about the principle of the photographing and imaging. So we start from the optics. So I'm not going to talk about that. So you can take a look by yourself. And Snell's law, like this, some people anyone choose the bathymetry paper? Yes. If you are talking about if you are doing presenting or doing the photogrammetry work, that is having that the light grade that path through different medium. In this case, you have different density. For example, air has a certain density, water has a certain density, and especially, for example, atmosphere has different density as well. And in this case, you have refraction to be considered if you are talking about precise photogrammetry work. So this Snell's law is Snell's law is for how to decide the refraction angle and incidence angle and also refraction angle as well. So that's one of the application in photogrammetry. And we talk about the lens, the rule of lens. So in the past, we talk about, say, do we really need lens? Maybe not. We can have something like pinhole camera. So, but however, so you can have you don't need a lens for a pinhole camera. However, that pinhole is too small. It's too small. So the problem of that is there's not much energy that you can get from a short period of time. So in this case, we want to increase the size of the aperture so that we can increase the shutter speed. We can increase the shutter speed. And in this case, that's the reason we need a lens because we need to be able to focus. Okay. So here it defines the optical axis, focal length, and also the curvature center of those lenses. So basically, it's like that. This is the lens formula for the thin lens. So this is kind of general. For example, like we have two distance over here. One is the object distance, which means that from the perspective center, perspective center to your object, and the other one is the image distance. It's talking about the principal point, the perspective center to your image plane. So that's one is called 物距, the other one is called 相距, right? And then the other one is focal length. So for the discussion of based on this, so as you can see, it's 1 divided by O, object distance, plus 1 divided by image distance equals to 1 divided by the focal length. So one thing that we can discuss over here is usually for the satellite, usually we will set the image distance, which means the perspective center to the image plane. We will usually set it as exactly the same as the focal length. Usually that's what we will do. So what's the reason for that? Usually we usually for the satellite camera, we usually set the image distance as the focal length. What's the reason for that? Do?